So, today I want to discuss the Fourier series and how one may arrive at it naturally through this differential equation. So let's just get straight into it, right? First of all, when solving something like this, we're going to want to determine what lambda is. I mean, it's simply a constant I've defined it as. So is it positive? Is it negative? Is it zero? Well, let's start with zero. If it's zero, then we can naturally find that this function u is going to evaluate to a linear function, ax plus b, something like that. So that satisfies the first boundary condition, but the second, if it starts at the origin and it's linear, then it's not going to be able to go back down to zero, is it? I mean, if you imagine like a straight line, if it starts at zero, it's never going to be zero anywhere else. So that, not that will leave us with a null solution, a trivial solution. Same with if we pick a positive value of lambda, that's going to give us a hyperbolic trigonometric function, which are not oscillatory. And so if it starts at zero, it's not really going to ever be zero again. So that will also lead us to the null solution or the trivial solution, and so we conclude that this must be negative. Now, with our typical differential equation solving methods, we are going to make this a square because we're going to have to square root it eventually, so it just makes notation a little simpler. So from our standard methods, we arrive at, note that I'm not going to use u for this, I'm going to use another letter, I'm going to use psi. Psi of x, which will become clear later, is equal then to a cosine kx, because I've defined lambda as minus k squared, given what I mentioned before, plus b sine kx. Now if we impose our boundary conditions, one will find that a goes to 0 and that b sine kl is equal to 0, which implies that k is going to be n pi over l, because sine is 0 at integer multiples of pi. So that leaves a solution psi of x is equal to b sine n pi x over l. And most first year physics classes will leave it to that as the solution to the differential equation, but some of the more astute amongst you may consider that this is not one solution. I mean, we're dependent on x, obviously, but we're also dependent on n here. I mean, it could be n equals 0, 1, 2, 3, 4, 5, So what would the most general solution be? I mean, a solution could be any combination of these functions. And so we call these psi functions the basis functions of this space. So we consider the most general solution u, which is what the original equation considers, is just a linear combination of these basis functions. Any possible function that satisfies this differential equation, where we have minus k squared, will just be a sum of these basis functions. And that makes sense now. I mean, this differential equation, if it gives us a cosine kx plus b sine kx, can produce any oscillatory function ever. I mean, any oscillatory function, any function with a period, can be represented as a sum of sines and cosines. And so here you can see the basis of the Fourier series being set up here. I mean, a Fourier series allows us to create any periodic function just by summing together sines or cosines. And here we have a differential equation that can produce any oscillatory function. And now we're trying to put together something that will help us actually find those, actually define those. So we have this, right? And you may be wondering, what can we do next? Well, I'm going to rub this out actually, because I don't want to use the entire board. I feel like that's going to be a bit messy and confusing. So we have oh, my pen's running out. Hold on. And I am back, sorry about that, with a new pen. U of x is equal to the sum So I say the first thing we do is try to look for a way of defining b, because if we're looking for a way to define a periodic function, this mysterious b is as a coefficient is going to give us trouble because we can't define it. So now we're going to consider the inner product. The sign basis functions are called orthogonal, which means that if we take the inner product of sine of index n and sine of index m, we're going to get the Kronecker delta of n and m, which means that if n is different from m, then we're going to get 0. Just like if you take the dot product of x hat and y hat, you get 0. But if you take the dot product of x hat and x hat, you get its length 1. But these are not orthonormal like those basis vectors. These are just orthogonal, so they don't evaluate to 1 in terms of length. Anyway, so we're going to take, oh no, my pen. Again, okay, it should be fine. So u and sine of m pi x over l yields us with bn, and then the length divided by 2, and the Kronecker delta. So, with this sum here, if you can see, I hope you can see, it's cycling through every m, and it's going to always be 0 until n matches what m is, at which point it's going to give the result of bn l over 2. So this sum effectively disappears, and we're left with one term. Now this inner product is simply an integral, so that's sine of, we're going to relabel the index back from, actually we can keep it as m, that's fine actually, there's no need to relabel it. M pi x over l u of x dx is equal to bn l over 2. Now we can just rearrange for bn, and we have bn is equal to 2 over l, between 0 and l, of sine of m pi x over l u x dx. And so now this bn, we can just relabel the index now to n, because they're the same idea, right? Now this goes in there and we have a full expression, but you may be questioning, there's a u here and there's a u there. How is u defining itself? Well, now we've come across the Fourier series. Now, u can be any function. It could be x, x squared, it could be e to the x, it could be anything. And it will be exactly equal to this series with itself, which is a bit of an abstract thought to think about. But it makes more sense if we replace the summation bound with a finite number. Oh, my pen's really not happy. A finite number like m I'm trying to write there. Yeah, this pen is pretty much gone. If we replace it with some finite number, so some large number m, and replace this with, say, a capital U, then this becomes a Fourier approximation of u of x, So that will give the function, say, if u of x is equal to x, your diagonal line, it's going to make that function periodic in L. So after L units, it will repeat. And the higher m is, the closer it will look like to L, and the lower it is, the more squiggly and more wavy it will be. And so you can kind of think of the Fourier series as analogous to a simple power series. A power series works in the basis of, x squared, x cubed, whatever. You have a coefficient times x to the power of n. Any function could be represented as that. Similarly, any periodic function can be represented by simply a sum of sines or cosines, as we've demonstrated here. Although it is a little more abstract to get to that, but we arrive at it nonetheless. So yeah, that it was important to show this visually, because just looking at maths on a whiteboard, it doesn't allow for much visual understanding. And so here we have a copy of exactly what I was writing on the board, complete with our function u of x equals x. And you can see this Fourier series of merely 10 terms does emulate, the function x quite well. Between the length specified, where L equals 1 in this case. But realistically, it could be anything. And so as m goes off into infinity, one will see that this function will approach exactly the y equals x line. And I think it's also important to say that whilst we've used the basis of sine here, the basis of cosine works equally well if we set the boundary conditions to be instead u of 0 equals 1. You can see that then it would start, or perhaps not 1, but the maximum amplitude of the function. So I haven't really thought too much about that, but I'll, well, I suppose I'll have to. And I suppose another way one could extend this is with merely using the complex exponential rather than the trigonometric functions themselves. You could get an even more general formula, but I thought I would present the idea behind it here, and then you can go off and have a look at it yourself.